Okay, so in this video, we're going to talk a bit about how to determine if a chemical equation is actually balanced. So, remember the law of conservation of mass. Again, hello, welcome back. Law of conservation of mass. Still using it. So remember, matter is neither created nor destroyed in a chemical reaction. So if we want to accurately apply the law of conservation of mass to our chemical reactions, this means that we need to make sure we have the same number of atoms of each type in both the reactants and the products. So we actually know a chemical equation is properly written and balanced if the chemical equation demonstrates the law of conservation of mass. Again, that would mean we have the same number of each kind of atom in the reactants and in the products. If there are not the same number of each kind of atom, the chemical equation is unbalanced, and again, it does not actually reflect how chemistry is happening in the real world. And we want our chemical equations to be accurate models to the best of our abilities. So let's gain those skills on thinking about balancing chemical equations. So we want to talk about some steps to take to know if a chemical equation is balanced. Pretty straightforward. Count the number of atoms in the reactants, count the number of atoms in the products, and then just compare. If you have the same number, it's balanced. If you have a different number, it's not balanced. So let's work through a couple of problems here. I'm going to do the first two written out on the screen, and then after that, I'll just talk about 3 and 4 out loud. So if I am looking at the first equation here, I have 2 water molecules, again, decomposing into 2 hydrogen gas molecules and 1 oxygen gas molecule. So I'm going to make my lists first. In my reactants, I have hydrogen and oxygen. In my products, I have hydrogen and oxygen. And then I'm going to fill this out and see if I have the same number of each. So if I'm looking at this, I have 2 water molecules. Each water molecule contains 2 hydrogen atoms. So if each water molecule contains 2 hydrogen atoms, that means I have 4 hydrogen atoms, 2 from each molecule. If I'm looking at oxygen, I have 2 oxygen molecules, or 2 water molecules, so therefore I have 2 oxygen atoms. So 2 oxygen atoms, 1 coming from each of my water molecules. So if I move to the products, I have 2 H2 gas plus O2. So if I want to know how many hydrogen atoms I have 4 hydrogen atoms because I'm getting 2 hydrogen atoms from each of those 2 H2 molecules, 2 from each molecule, and I have 2 molecules, lots of 2s. And then I have O2 gas, so I have 2 oxygen atoms coming from the 1 oxygen molecule I have. So that means this checks out and is balanced. Yes. So this chemical equation is balanced. Okay, let's go ahead and look at the second one. Sneak peek. So let's go ahead and look at the second one. So I'm going to write down and make my lists first and determine what kinds of atoms I have, then I'll count them. So here I have sulfur gas reacting with fluorine gas to make sulfur hexafluoride. So in this case, we have sulfur and fluorine in our reactants, and I only see sulfur and fluorine in my products. So now I need to count them up and determine if this follows that law of conservation of mass because it has the same number of atoms on the left-hand side as it does on the right-hand side. So I see that I have 1 S8 molecule, so if I have 1 of those, I have 8 sulfurs. If I'm looking here, I see that I have 1 fluorine gas molecule, so that means I have 1 fluorine with 2 atoms in it. So I have 2 fluorine atoms. And then I look to my products, and then I see I have 1 SF6 molecule, so that means my subscripts are going to represent the number of atoms of each I have. So I have 1 sulfur and 6 fluorines. So this is not balanced. So unbalanced, not balanced. I don't mind either way. I will just say not balanced. because sometimes those prefixes get a little like hard to hear. So I'm just going to say it's not balanced or it's unbalanced. So no, sad face. It's not balanced. It doesn't follow, therefore, the law of conservation of mass as it is written. However, do remember that we will talk a bit more about how to balance equations in just a few seconds here. So again, no, this is not balanced. We see that we have different amounts of both sulfur and fluorine in the reactants as we do the products. So no, it's not balanced. If I'm looking down here at the bottom, something that you can do is kind of follow this little bit of an algorithmic strategy. So we don't want to waste any time on these problems that we don't need to waste, right? So if I'm asking you if something's balanced or not, a simple yes or no question, what I need you to do is look at the equation and just start. I generally start from the left-hand side. I start counting atoms. The second I run into something that is not balanced, boom, check, done. Nope, not balanced. Because if even one of them does not have the same number of atoms on both sides, it's unbalanced, period, and you have to fix it eventually. So, that being said, let's go ahead and take a look at number 3 down here. So, I'm going to look at the carbon first and foremost. So, carbon's my first atom. I'm going to look at the carbon. If I look at the carbon, I see on the left-hand side, I have one C2H6 molecule. So, if I have one C2H6 molecule, that means that I have 2 carbon atoms. So if I check out my entire left-hand side, I have 2 carbon atoms. And if I check out my right-hand side, I just have 1 carbon dioxide molecule. So that means I have 1 carbon in the products. So I already know I don't need to keep going. 2 carbons versus 1 carbon, not the same number? No, that's not balanced. I'm not going to keep counting. It's a waste of my time to see if the other ones are balanced, because if even one isn't balanced, doesn't matter. So let's go ahead and try number 4. Number 4 says potassium iodide reacts with lead 2 nitrate to make lead 2 iodide and potassium nitrate. So if I'm looking at that potassium first, the K, and I find K on both sides, I got 1 potassium on both sides. I'll keep going. I look at the iodine. I see I have 1 iodine in the reactants, and I have 4 in the products. Nope. I'm getting 2 iodines in the products from each lead 2 iodide molecule. So therefore, if I have 2 molecules and I'm getting 2 iodides from each molecule, I have 4 of those kinds of atoms. So I went from having 1 to having 4. Nope, not working out. So we're going to go ahead and need to eventually balance this because it is unbalanced. So the thing is that if you want to confirm that it's balanced, you have to check every kind of atom. So you can't just stop after you read potassium, obviously, because potassium's balanced, but that doesn't mean that everything else in there is balanced as well. So that being said, to confirm that it is balanced, you have to check every kind of atom and confirm that they are not, that they have the same number of atom in both the reactants and the products. But if you run into one that's unbalanced, you can just kind of stop there. So you have to confirm that all of them are balanced to say that the equation is balanced. But if you run into an issue, you can stop before then. So I'm going to leave you with some practice on this subject as well, so you can work through these practice problems. And of course, I have some explanations in the slides as well. So go ahead, check those out, get some practice in, and then come back when you're ready to talk about balancing chemical equations. All right, so we talked a little bit about being able to check to see if equations follow that law of conservation of mass or don't, so whether they're balanced or whether they're unbalanced. So what do we do if they're not balanced? What do we do if these equations don't follow the law of conservation of mass? We call the act of making sure there are the same number of atoms of each type on both sides balancing the chemical equation. So we did use that word balance a little bit before when we were talking about having equal amounts of positive and negative charge in our ionic compounds to like kind of cancel out the charge. we're kind of using it in the same idea here. We got to have the same number of atoms on both sides. So like I'm using the word balance to mean the same number of in this case. So same number or same idea here, but instead of worrying about charges, we're worrying about total numbers of atoms. So while there are a few things we're going to need to remember on the way, it's kind of a straightforward concept. Use the coefficients to equalize the number of each type of atom. There will be different balancing skills and steps we have to follow depending upon the type of equation we run into, but for right now, we're going to talk about one kind of equation in general, which we'll talk more about in the next video, precipitation reactions, those ones that we did in lab where the solid falls out of solution. There'll be a few different things we got to remember along the way. There'll be different skills for different types of equations. However, we're going to kind of do the most straightforward piece right now, and we will pick up some more of those skills as we talk about those different kinds of equations, especially, I will say, when we get down to the last 4 chapters, which are kind of our survey of chemistry, all the different kinds of chemistry we can be doing. When we get there, we'll talk a bit more about balancing those kinds of equations. But for right now, we're just going to look at some pretty straightforward examples. So now that I put this on the screen, it doesn't seem quite so straightforward. However, once you kind of hear what I have to say, it's got just a lot of background work and then some easy stuff from there. So steps to balancing chemical equations. You gotta start with counting the number of each type of atom on each type or on each side of the chemical equation. So the thing we just practiced, counting up the number of types of each atoms you have on each sides, and then you can determine if it's balanced or not. If the equation's already balanced, stop. There's no reason to continue on, don't pass go, don't collect $200, go directly to jail, stop. No, I'm totally kidding. So if it's already balanced, you just don't have any more work to do. However, if you count the number of atoms of each type on both sides of the chemical equation, and you see that they are not equal, you got to continue on to balance the equation. So from there, we just kind of look at which types of atoms are uneven from each other, and we add coefficients to balance the number of types of each atom. So I've got a small, little list of guidelines to follow. It's not as strict here when we're balancing chemical equations. It's just kind of like sometimes you get this gut instinct, this feel. Once you start to practice over and over and over again, you'll be able to really nail down kind of when some of these should be applied, when they can't. So we'll get lots of practice in on this kind of stuff. So you may need to add multiple coefficients. So you may have a coefficient on one molecule in the reactants. You may have multiple molecules with coefficients. You may have molecules with no coefficients, kind of a deal. So you may have to add more than one coefficient, or you may need to add just one or something like that. So don't be afraid to try to add more than one coefficient. What you should do is try to balance metals first, then nonmetals. I'm sorry, there's a small typo on your screen. So try balancing metals first, then nonmetals. If you see an element by itself, it's a free element, so balance that last. And if you end up with a fractional coefficient somehow, multiply the whole equation by the denominator to clear the fraction out. We'll talk about that. We'll talk about these steps. I'll bring them up again as we start working through the problems, but here's a first and foremost statement for you of what they are. So once you finish, every time, I need you to go back and check your work by counting the number of each kind of atom in the reactants, counting the number of each kind of atom in the products. That way you can determine if it's properly balanced. Go back and check. Go back and check your work when you're done. I noticed as I was going back through these that there were certain places where I had missed writing in a coefficient. Like there were 3 coefficients in the equation and I was missing the 4th because it was a typo. I just hadn't done it. If you go back through and you recount everything, you're not going to have typos. You're going to know you have the right answer in the end. So, in summary, you count the number of each type of atom in the products and the reactants, and you use coefficients to increase or decrease the number of copies of a whole molecule you have, so that you have the same number of each type of atom in the reactants and the same number of type of each atom in the products. So, things to look out for. These are like things we cannot do. These are the no-goes. These are, please, I swear, do not do them. So you cannot change subscripts. you cannot change the subscripts. Why? Because when we're writing a chemical formula, remember, the chemical formula, the actual molecule you have, is designated by those constituent elements and their ratios to each other. Remember, H2O is much different than H2O2, okay? So we know water and hydrogen peroxide are very different. So if we were trying to balance an equation with water in it, and we changed the subscript on oxygen to O2, we now have an entirely different compound than what we were originally talking about. Before we were talking about water, now we're talking about hydrogen peroxide. So you cannot change the subscripts. Remember, when we're looking at a chemical equation, we're looking at a specific set of reactions of a specific set of elements together. So if you change the subscript, you change the identity of the chemicals you're reacting. You're no longer talking about the same thing. I don't know what equation you're balancing if I asked you to balance something else, therefore. So do not change the subscripts, because then you change the identity of the chemicals you have. And you do not want to do that. We want to look at the chemical reactions in question. Thing 2, your coefficients should always only be divisible by 1. So basically, if you can simplify the coefficients by dividing all of them by the same number, do it. As long as it's not 1. I mean, if you divide them all by 1, you'll get the same thing anyways. But if you can simplify it by dividing all of them by a number other than 1, do it. So I have written here on the screen, 4H2 plus 2O2 yields 4H2O. Well, I could divide each of those coefficients by 2, so I should do it. Absolutely. So it should really be 2H2 plus O2 yields 2H2O. So you don't want to leave unsimplified coefficients. You want to make sure they're the lowest number possible. And I mentioned this before, but I would like to point it out one last time. So no fractions are allowed in the final answer. So sometimes along the way, it can make it easier to balance the equation if you use a fractional number. But if you choose to do this, you should be sure to multiply through by the denominator of the fraction to clear it out. So we may also write this equation like so. So if we counted this out, we would find that it's a balanced chemical reaction. However, it's not really properly written. What we should do is multiply each of the coefficients by 2, which happens to be the denominator of this fraction. So multiply each of those by the denominator of the fraction, which happens to be 2. So that you get 2H2O2, 2H2O again. So we multiplied each coefficient by 2 to clear out that fraction. I'm not likely going to give you examples where I use fractions to balance. I'll show you how I kind of work around that. However, I highly encourage you guys at all times to seek out whatever resource makes sense for you. So if you find YouTube videos that show you how to balance chemical equations with mathematical equations, I've done that in math class and in coding classes before. I don't care, do it. If you know how to balance chemical equations in another way or another professor showed you, go for it. I don't care. If you find, again, any YouTube videos, please go out, seek them out. If what I'm saying doesn't make sense to you, find other resources. But you just have to make sure that you're still getting to the right answer in the end. So you can't just like leave something like this fraction cleared out or something unsimplified like this. So tips and tricks. So here is kind of the little thing you keep in your back pocket where you're like, I think I can do this. I think I can do this. So first and foremost, again, start with metals over nonmetals. So it's kind of that idea of work from the bottom left-hand corner of the periodic table up to the top right. Your life will just be easier. My answer to all of this is your life will be easier if you follow these tips and tricks. If not, I think you're going to get really frustrated by balancing chemical reactions really fast. So start with metals over nonmetals. Leave hydrogen and oxygen for the end. So I would do oxygen before I did hydrogen, but leave those two for the end. They kind of come along the way. So once you're figuring out the coefficients of the other elements, it'll start to come along the way that your hydrogen and oxygen follow along most of the time. A lot of times they're also split between multiple compounds, and that can be really hard. So that's like my tip number 3. If you see an element in more than one compound, so you see that you've got, let's say, carbon dioxide and water, both of those contain oxygen atoms. So I would leave oxygen for last because it's contained in 2 different compounds. It's a little complicated. Hopefully it'll come along the way. I'll save it for last. And if you see a free element, save it for last as well. So what's a free element? It's just the element standing by itself with nothing else in the chemical equation. So we were looking at this reaction here. Oxygen and hydrogen are considered to be free elements over here in this case, and then this is not. So these are not free elements. However, this is a free element and this is a free element. So is it standing by itself, where when you adjust the coefficient, the only thing you are adjusting is one type of atom. That's kind of what a free element is. So it's really easy to balance those because you can put a coefficient in front of the freestanding element. So it's much easier to leave them for last and kind of like pick up the slack once you get there. So I'm going to work through some problems here with you. I'm going to work through some examples and let's get going. I'm going to write out some work by hand as well as we work through this. So we have, Okay, so we're going to go ahead and balance this chemical equation. So we see the H2 gas is reacting with the chlorine gas, Cl2, to give us HCl. So first and foremost, we need to determine if this is a balanced chemical equation. So the first thing I do is I look at the original problem and I count the number of each kind of atom in the original problem. So I have hydrogen, I have chlorine, I have hydrogen, I have chlorine. I'm going to write out which kinds I have in the reactants, which kinds I have in the products. Then I'm going to count them up. So I look at my reactants and I have no coefficient as of right now. My blanks are where we will eventually determine the coefficient of. So I have no coefficients right now, so I have just one of everything. So I can just use the subscripts to inform which kind of atom I have, or how many of each kind of atom I have. So I have H2, which means I have 2 hydrogens. I have Cl2, which means I have 2 chlorines. So in that case, I have 2 hydrogens in the reactants, 2 chlorines in the reactants. Now I'm going to go to the products. It looks like I just have 1 HCl molecule, so I have 1 hydrogen, 1 chlorine. Well, when I take a look at this, I look at my original problem and I say, is it balanced or not? No, it's not balanced. I can clearly see that I have a different number of hydrogens and a different number of chlorines in my reactants. So the first thing I'm going to do is I'm going to try adding a coefficient 2 in front of HCl. So what I'm looking at here is this. I think, okay, I have 2 hydrogens, 2 chlorines. Chlorine, I'm going to go for first because I try to leave hydrogen for the end. So I'm going to try chlorine first. So I see I have 2 chlorines in the reactants and only 1 in the products. So I find chlorine in the products and I add a coefficient in front of there. So again, I'm going to see what happens if I add a coefficient of 2 in front of HCl. Well, I'm going to count up what I have. I know I haven't changed the reactants, so I still have 2 hydrogen atoms, 2 chlorine atoms. However, I did change the number of each I have in the products. So if I increase to having 2 entire copies of the HCl molecule, I have therefore 2 hydrogens and 2 chlorines. I recount up. I see I've got 2 hydrogens, 2 chlorines in the reactants, 2 hydrogens, 2 chlorines in the products. I'm balanced. H2 plus Cl2 yields 2 HCl. There you go. What we've done so far is count up the number of atoms we have in our original problem. So the next thing I need to do is try to place a coefficient to see if I can't start to balance something. I'm looking at the kinds of elements I have. I have carbon, I have hydrogen, I have oxygen. In our kind of tips and tricks, what we think about is that we leave hydrogen and oxygen for last. So let's try to do the carbon first. So if I have 7 carbons on the left-hand side and I have 1 carbon on the right-hand side, I'm going to try to put a 7 in front of the carbon dioxide and the coefficients. That way I can try to have 7 carbons on both sides. So I didn't do anything to the reactant, so I'm not going to recalculate there. But let me triple check how many of each kind of atom I have in my products. So if I want to know how many carbons I have, it looks like I have 7 carbons. If I want to know how many hydrogens I have, it looks like I have 2. And then it looks like I'm getting 1 oxygen from the H2O and then 14 oxygens from my 7 carbon dioxide molecules. So if I have 2 oxygen atoms and I have 7 molecules that contain 2 oxygen atoms, I've got 14 oxygen atoms coming from there. So I have 15 oxygen atoms total. So now that I have my carbons balanced, I'm going to try to decide, should I do hydrogen first? Should I do oxygen first? Well, as I'm looking at this problem here, I think I would go for doing hydrogen first. And this is why. Because oxygen exists as a free element here. So oxygen exists as a free element, so it's going to be much easier if we leave oxygen for last in this case. So therefore, let's go ahead and try to take care of the hydrogens. So it looks like on the left-hand side, I have 8 hydrogens. On the right-hand side, I have 2. So I'm going to go ahead and place a 4 in front of the molecule in the products that contains hydrogen. That way, when I recalculate, I can say, okay, I've got 7 carbons. I have 4 molecules of H2O. So that means I have 8 hydrogens, getting 2 hydrogens from each of my 4 molecules. And I have 4 oxygens coming from that molecule, and then I have 14 from my other, so now I have 18 oxygen atoms on the right-hand side. Again, 14 from the carbon dioxide, 4 from the water, so 18. All right, let's make another pass over this and see what happens. So looks like I've got 7 carbons. I've got, on both sides, I've got 8 hydrogens on both sides. I'm just left to deal with that oxygen. However, because oxygen's freestanding, I should just be able to adjust the coefficient in the reactants to take care of this. So if I want 18 oxygens on the left-hand side, I'm going to need to put a 9 in front of my oxygen. So I have 9 times 2 oxygen atoms, which is 18. So I'm going to recalculate in my reactants to triple check I have everything I need. Looks like I have 7 carbons, I have 8 hydrogens, and I have 18 oxygens. So when I triple check my answer here, it looks like I've got the same amount of both, so therefore I have balanced my chemical reaction. So that one's a little more complicated. We needed to use a few more coefficients to get there. We had to kind of stop and rethink. So the way these problems kind of work is it is kind of a stop and rethink. It's like, let me try this, see what happens. Let me try that, see what happens. There's like, again, very, very like kind of good guidelines you can follow, but it's not as strict as some of the other processes we learn in chemistry. This kind of becomes a little bit of a feeling thing, a little bit of I know how to work through this kind of a deal. But if you think about doing things like leaving hydrogen and oxygen for last, leaving any freestanding elements for last, it makes the whole process go just a bit smoother. So that is how we balance this reaction. So we're going to go ahead and work through our second example here. So we need to balance this chemical equation. So the first thing I am going to do is list all of the elements I see on the left-hand side, all of the elements I see on the right-hand side. So in the reactants, I see carbon, I see hydrogen, I see oxygen. And in my products, I see, again, carbon, hydrogen, oxygen. I'm just going to make sure I write them in the same order so it's easier for me to see in a minute. So if I'm balancing this chemical equation, what I need to do is start to count up how many I have on the left-hand side, how many I have on the right-hand side. So if I have C7H8, it has no coefficient in front of it. I have 7 carbons and 8 hydrogens. If I'm looking at my oxygen, it also does not have any carbons in front of it, so I can just look, or any coefficients in front of it, so I can just look at the subscript. So I've got a subscript of 2. So I have 7 carbons, 8 hydrogens, 2 oxygens on the reactant side. If I go to look at the product side of the arrow, I see I have 2 hydrogens. Looks like I've got 1 carbon, and then I've got oxygen contained in both the water and in the carbon dioxide, so I have to make sure I count both, so I have 3 total oxygen atoms. Okay, so we're going to go ahead and balance the chemical equation that you see on the screen here. This is going to be the most complicated example that we're going to do, and then I have some things written out in the slides for you that you want to take a look at, give some practice for you there, as well as some practice problems for you to look through. So let's go ahead and work through this problem. So I already have written on your screen here all of the different elements that I see on each side of the reaction. So in the reactants and in the products, I have all the different kinds of elements I see listed out. So that's lithium, sulfur, potassium, phosphorus, and oxygen. I've just written them in the same order on both sides. So remember, the first thing that we need to do is count the number of each kind of atom we have. So we don't see any coefficients. We can just look to the subscripts to inform our counting. So that means I have 2 lithium, 1 sulfur. I'm going to leave the oxygen for a second. I've got 3 potassiums, 1 phosphorus, and then I have oxygen in both my compounds, so I have 8. If I look to my products, I see that I have 3 lithium, 1 sulfur, 2 potassium, and 1 phosphorus, and 8 oxygens. So if I kind of take a look at the list the way it's written, it looks like up front I'm mostly concerned about the lithium and potassium. So they're both metals, so I would start with them anyways. So I think the first thing I'm going to do, and you could choose any of the compounds that contains a metal, which is any of them this time, that's not freestanding, which we have no freestanding elements in this one. But what you might do is something like this. I'm going to try putting a 2 in front of lithium. So what I'm thinking about here is that I have a coefficient of 2, or a subscript of 2 that leads me to know that I have 2 lithium atoms in my reactants. So I'm going to try adding a 2 in front of that compound. I'm choosing to do a 2 because in my mind, my next step is going to be put a 3 in front of the lithium with a subscript of 2. So I'm kind of basically going to say, okay, if I've got 3 over here, if I multiply it by 2, I'm going to get the same number as if I've got 2 over here and I multiply it by 3. So I don't know. So I'm going to try putting a 2 in front of lithium. So if I go back through and I count my number of atoms, I didn't change anything in the reactants. I'm going to recount in the products. I now have 6 lithium. I have 2 phosphorus. I have 1 sulfur, 2 potassium, and then I'm getting 4 oxygens from my K2SO4, and then I'm looking to get 8 from here because I've got 2 copies and I have 4 oxygens per copy. So there I have 8 and 4 is 12 oxygen atoms on the right-hand side. So now, as I mentioned before, I'm going to go ahead and put a coefficient of 3 in front of the lithium sulfate. So I'm going to go ahead and recalculate. So basically, I could have added these both at the same time in one step, but I just want to break it down, make it exactly like apparent what I am doing every step of the way. So I have 6 lithium. I now have 3 sulfur. I'm going to leave the oxygen for a second. I have 3 potassium, 1 phosphorus, and then it looks like I'm getting 12 oxygen atoms from the lithium sulfate, and I'm getting 4 oxygen atoms from the potassium phosphate. So that leaves me with 16 oxygen atoms. Okay, so my lithium's balanced. I need to do my potassium too. So let's try to get that potassium balanced. So what I'm going to do is put a 3 in front of the K2SO4 by the same logic that I held with the lithium, that it will likely just be easy to try to multiply it together to get where you're going. So I'm going to put a 3 in front of potassium sulfate. If I put a 3 in front of potassium sulfate, I'm going to recalculate in my products. So it looks like I have 6 lithium, I have 2 phosphorus, I have a certain number of oxygens, we'll come back. Looks like I now have 6 potassium, and I now have, that's my bad. I just did that in a different order. It should be 2 phosphorus, and then I have 3 sulfur. My bad, guys. 2 phosphorus, 3 sulfur. So 2 phosphorus, 3 sulfur. And then I'm going to come back and grab my oxygens. So I go from having 8 oxygens from my lithium phosphate, and then I'm also going to get 3 from my potassium sulfate. So I now have 20 oxygen atoms because I'm getting 12 and 8 is 20. 8 from the lithium phosphate, 12 from the potassium sulfate. All right, let's go ahead and put a 2 in front of the potassium phosphate in the reactants to see if that helps us on our quest to balance. So I'm going to recalculate in the reactants again. So this means I have 6 lithium, I have 3 sulfur. I'm going to do potassium and phosphorus next. So I've got 6 potassium, 2 phosphorus, and I have 12 oxygens from the lithium sulfate and 8 oxygens from the potassium sulfate. So I have 20 oxygen. So once I've done this, if I check out what I'm left with, looks like I've got 6 lithiums in both cases, checks out. Looks like I'm left with 3 sulfurs, each checks out. Looks like I'm left with 6 potassiums on both sides. Looks like I'm left with 2 phosphoruses on both sides and 20 oxygens. So I would say this is balanced. So our final equation is with these coefficients as what you see on the screen here. So I'm going to leave these as examples for you to work through. I've tried to set it up so that you can see some of the work. If you are confused along the way, these are the steps I would take. This is how I would do it. So it should be broken down there. So I've left you with this, but I've also left you with this really awesome website. So I know it's not just in the PowerPoint for you. I know you got to go click the link and go to another website. However, please, please, please go check this out. Honestly, it's a really nice website. It explains a ton of stuff. If you haven't tried to work through the problems on the website, it's got a lot of examples and it has explanations for all the reasoning behind all its different examples. So please check that website out. It is kind of ugly, I will admit, but if you need some practice and you want some explanations and examples, that is the place to go. So that is our work on balancing chemical equations. Let me know if you have any questions.